The process begins with high-quality aluminum chosen for its lightweight properties, strength, and resistance to corrosion. Unlike cast wheels, which are made by pouring molten aluminum into molds, forged wheels are created from a solid piece of aluminum. A large billet of aluminum is cut into smaller cylindrical sections known as blanks or preforms. Each blank is precisely measured to have just enough material to form a single wheel. The aluminum blanks are placed inside a high-temperature furnace, where they are heated to approximately 500 degrees Celsius, 932 degrees Fahrenheit. This temperature is high enough to soften the aluminum for the forging process, but not hot enough to melt it. The purpose of this step is to make the metal more malleable so it can be shaped without cracking. The blanks remain in the furnace for about 2 hours, ensuring uniform heating. Once heated, the softened aluminum blank is transferred to a rotary forging press. This press exerts extreme pressure, typically around 4,000 tons, to shape the aluminum into a disc. This process not only reshapes the metal, but also alters its molecular structure, making it denser and stronger. The forging process aligns the grain structure of the aluminum, significantly improving its resistance to impact and stress compared to cast wheels. The result is a lightweight yet highly durable wheel blank. After the initial forging, the aluminum disc is placed onto a shaping machine. Here, massive computer-controlled rollers descend onto the disc, applying pressure while spinning it at high speeds. As the aluminum is stretched and thinned, it gradually takes the shape of a wheel rim. Cooling liquids are usually sprayed onto the metal to reduce friction and prevent overheating. In just 45 seconds, the flat disc is transformed into a wheel up to 40 centimeters, 16 inches high. To further enhance the wheel's strength and durability, it undergoes another round of heat treatment. The newly formed rims are placed inside a furnace, where they are reheated to around 530 degrees Celsius, 986 degrees Fahrenheit. This process is known as solution heat treatment and serves to refine the internal structure of the aluminum. Immediately after heating, the wheels are rapidly cooled in a quenching bath filled with cold water. This sudden cooling locks the refined molecular structure in place, increasing the wheel's toughness and resistance to fatigue. After cooling, the wheel undergoes CNC, computer numerical control, machining to achieve precise dimensions. High-speed cutting tools are used to carve out the spoke design. This is both aesthetic and functional, as open spaces between spokes improve airflow and help cool the brakes. Cut bolt holes. These allow the wheel to be securely attached to the vehicle. Trim excess material, ensuring the wheel is lightweight without compromising strength. The machining process ensures that the wheel meets strict tolerances for balance and roundness. Before a wheel rim is approved for use, it must pass rigorous quality control tests. Sensors and laser measuring devices check for roundness. An uneven wheel can cause tire wear and unsafe driving conditions. Structural integrity. The wheel is subjected to stress tests to ensure it can withstand heavy loads and impacts. If any defect is found, the wheel is rejected or reworked. If the wheel passes inspection, it is polished to a high shine using buffing machines. The process begins in the foundry, where molten aluminum is carefully cast into molds in one of the 3 dedicated casting areas. This stage is crucial, as it determines the strength, durability, and overall quality of the wheel. GMP Italia produces 1,200 wheels per day, demonstrating the effectiveness of its manufacturing process. The production of an alloy wheel is a combination of advanced technology and expert craftsmanship. At GMP Italia, this process is highly industrialized and follows lean manufacturing principles to ensure both efficiency and high-quality results. The three casting areas in alloy wheel production at GMP Italia. The three dedicated casting areas are the foundation of the alloy wheel manufacturing process. Each area specializes in a specific casting technique to ensure precision, durability, and performance. These include low-pressure casting (LPC), enhances wheel strength by injecting molten aluminum into molds under controlled pressure. Gravity casting uses natural gravity flow for cost-effective production of robust wheels. Flow forming, a hybrid process that refines cast wheels for lighter, stronger, and more durable results. Once cast, the wheels go through 10 production stations where they are refined and perfected. This includes cooling, trimming, and machining to achieve precise dimensions. The wheels are then subjected to rigorous quality control checks to ensure they meet global standards for safety and performance. A key factor in GMP Italia's success is its commitment to technological innovation. By continuously investing in state-of-the-art machinery and processes, the company maintains a competitive edge in the global alloy wheel market. This dedication allows for the production of high-performance, uniquely designed alloy wheels that meet the needs of car enthusiasts and manufacturers worldwide. The wheel-making process has evolved significantly over the years, with automation playing a crucial role in improving efficiency, precision, and scalability. Modern wheel manufacturing relies on state-of-the-art machinery and robotics to streamline production, minimize human error, and enhance product consistency. The first step in the automated wheel-making process involves selecting the right materials. Depending on the application, manufacturers use various materials, including steel, aluminum alloys, carbon fiber, and magnesium alloys. Each material offers different benefits. Aluminum wheels are lightweight and corrosion-resistant, while steel wheels are more durable and cost-effective. Once the material is chosen, it undergoes preparation, which includes cutting large sheets or billets into manageable sizes using automated laser cutting or hydraulic shearing machines. In the case of alloy wheels, metal ingots are melted and cast into preliminary wheel shapes using high-precision furnaces and molds. Forged wheels are stronger and lighter than cast wheels. The process begins with a solid metal billet that is heated and then subjected to immense pressure using automated forging presses. This compression refines the grain structure of the metal, increasing its strength. CNC, computer numerical control machining, then shapes the forged blank into the desired wheel design. Flow forming is a combination of casting and forging. A cast preform is placed on a spinning mandrel, while automated rollers apply pressure to shape the rim. This process enhances the mechanical properties of the wheel while keeping weight minimal. Regardless of the manufacturing method, every wheel undergoes CNC machining to achieve exact dimensions and design features. Automated robotic arms hold the wheel, while multi-axis CNC machines carve intricate details, including bolt patterns and hub bore specifications. This step ensures the wheel meets industry standards for fit and function. The process of welding wheels is crucial for ensuring strength and durability. It begins with surface preparation, where contaminants like dirt and grease are removed using grinding or chemical cleaning. Next, automated welding machines, often using MIG or TIG welding techniques, fuse the wheel components with precision. The process is carefully controlled to maintain consistent heat and prevent material distortion. After welding, the wheels undergo stress relief treatments and thorough inspections, including X-ray or ultrasonic testing, to detect any defects. To improve durability, wheels undergo automated heat treatment processes such as solution heat treatment and aging. This step enhances the material's structural integrity, making the wheels resistant to stress and impact. After machining, wheels receive various surface treatments to improve their aesthetics and longevity. Automated processes apply protective coatings through electrostatic painting, powder coating, or anodization. Some high-end wheels undergo diamond cutting or polishing, using robotic polishing systems for a mirror-like finish. The first stage tire building machine is a critical part of the tire manufacturing process, responsible for assembling the green tire, the unfinished tire structure that serves as the foundation for further processing. Key components of the first stage machine: tire building drum, the central rotating platform where the tire components are assembled. Turret servicer, an advanced material handling system that efficiently feeds different materials into the process. Operator control panel with PLC system, a programmable control system that allows precise automation and adjustments. The process begins with the application of carcass ply layers, consisting of fabric-reinforced rubber. These layers are placed onto the building drum in either bias or radial orientations, depending on the tire type. The machine's double shaft system, operating at 110 revolutions per minute, ensures smooth material handling and minimizes downtime. Upper and lower stitching rollers press the layers together, eliminating trapped air and ensuring a firm bond. The rollers apply uniform pressure, improving the adhesion of different layers for better durability. Bead rings, which are made of reinforced steel wires encased in rubber, are placed at both edges of the carcass. These rings provide structural rigidity and ensure the tire maintains its shape. A pneumatic bead setting system, guided by linear rails, precisely positions the beads. The sidewalls are applied using 2 turning service tables, which ensure proper alignment and finishing. With the green tire fully assembled, it is transferred to the second stage tire building machine for further processing, including shaping, breaker placement, and tread application. The second stage tire building machine is a crucial part of the tire manufacturing process, refining and strengthening the green tire assembled in the first stage. This stage involves carcass shaping, breaker application, and tread placement, ensuring the tire achieves the required structural integrity, uniformity, and durability before it moves to curing. The process is highly automated, utilizing precision control systems from leading manufacturers like Siemens and Beckhoff. Key components of the second stage tire building machine: transferable shaft and disc plates, hold and shape the tire during the process. Stitching facility ensures tight adhesion of materials to prevent defects. Breaker servicer feeds and applies breaker belts to reinforce the tire. Strip winder applies tread material in a controlled manner. 1. Carcass shaping. The green tire from the first stage is mounted onto disc plates and inflated. A precise inflation and shaping mechanism expands the carcass into the required tire profile. This process is crucial as it ensures proper alignment for the upcoming layers. 2. Breaker belt application. Breaker belts, reinforcing layers made of rubberized steel or fabric, are fed from the breaker servicer and carefully positioned on the tire. These layers enhance the tire's strength, flexibility, and impact resistance, allowing it to withstand high speeds and heavy loads. The stitching facility then presses the breakers into place, ensuring optimal adhesion and eliminating trapped air. 3. Tread placement. The tread, which makes direct contact with the road, is applied over the breaker belts. There are 2 main methods for applying the tread. Strip winding. Thin rubber strips are precisely wound onto the carcass, allowing for accurate material distribution. Extruded tread application, optional. Instead of strip winding, pre-extruded tread rubber can be applied in one piece. 4. Final stitching and inspection. The entire assembly undergoes final stitching, where rollers press all layers together to enhance adhesion and eliminate voids. The machine's stitching unit moves in 3 different directions, ensuring full coverage and tight bonding. A final inspection is performed to verify that all components are properly positioned. Precision and automation. The entire process is highly automated, minimizing human error and ensuring consistency. Advanced PLC control systems allow operators to monitor and adjust machine functions in real time. Tire disposal has long been a challenge in waste management and recycling. Discarded tires take up excessive space in landfills, pose environmental hazards, and create fire risks. However, with advancements in recycling technology, tire baling has emerged as an efficient solution to this problem. One of the most effective machines for this purpose is the hydraulic tire baler REC 7242 terabytes. This powerful and efficient baler is specifically designed to compress waste tires into dense, manageable bales, optimizing storage, transportation, and recycling processes. The REC 7242 terabytes is a heavy-duty hydraulic tire baler engineered to compact and bale used tires efficiently. It is capable of compressing up to 91 mixed tires into a single 1838 lb bale, which measures approximately 72 inches 6 feet in length, 40 inches in width, and 44 inches in height. This process significantly reduces the volume of discarded tires, making them easier to store, transport, and recycle. The REC 7242 terabytes operates using high-pressure hydraulics to compress tires into dense bales. The process follows these key steps. Loading the tires. Used tires are loaded into the baling chamber. These can be a mixture of different sizes and types, including car, truck, and light commercial tires. Compression process. The baler applies significant hydraulic force, compressing the tires into a tightly packed bale. The hydraulic system ensures that the tires are pressed into a uniform shape, reducing their volume significantly. Binding the bale. Once compressed, the bale is secured using heavy-duty steel wires or straps to maintain its shape. Ejecting the bale. The completed bale is then ejected from the baler and is ready for transport or further processing in recycling facilities. The REC 7242 terabytes hydraulic tire baler offers numerous advantages in the tire recycling industry. Volume reduction. By compressing 91 mixed tires into a single bale, the machine reduces storage and transportation costs significantly. Efficient transportation. The compact bales make it easier to transport large volumes of tires to recycling plants, reducing logistics costs. Environmental benefits. Properly baled tires minimize the risk of illegal dumping, prevent mosquito breeding grounds, and lower fire hazards. Space optimization. The bales occupy far less space than loose tires, making storage more efficient. Improved recycling process. Tire bales are easier to handle, shred, and process in recycling facilities, making them an essential step in sustainable tire disposal. Applications of baled tires. Once tires are baled using the REC 7242 terabytes, they can be used in various applications, including rubber recycling. Baled tires are transported to recycling plants, where they are shredded into rubber chips for reuse in asphalt, playground surfaces, and other rubber products. Fuel for cement kilns. Some industries use whole or shredded tires as an alternative fuel source due to their high energy content. Civil engineering projects. Baled tires are sometimes used in construction projects, such as road embankments, erosion control, and sound barriers. Exporting for recycling. Many countries with established tire recycling programs import baled tires to process them into reusable materials. Fetch preform from oven. Using heat-resistant gloves or robotic arms, carefully remove the heated preform from the oven. Ensure the preform has reached the optimal forming temperature before proceeding to the next stage. Spray or immerse the preform's face to rapidly cool it. Stretch and shape the rim using high-pressure rollers, refining its structure, reducing thickness, and enhancing strength for optimal performance and durability. Apply graphite lubricant to tooling for smooth forming and reduced friction. Position the heated preform onto the machine's tooling for shaping. Move the preform carefully to the oven using a conveyor or robotic arm, ensuring even heating for optimal material workability and strength. After the flow forming process, submerge the rim into a cooling tank filled with a controlled coolant, such as water or oil. This rapid cooling stabilizes the material structure, relieves internal stresses, and enhances mechanical properties. Proper cooling ensures dimensional accuracy, prevents warping, and prepares the rim for further processing or finishing. Flow forming is an advanced metal forming technique used to manufacture high-strength, lightweight wheels. The process begins with a preform, a partially cast or forged wheel blank, which is heated to an optimal temperature for shaping. Once heated, the preform is placed onto a rotating mandrel, where high-pressure rollers gradually stretch and compress the metal. As the rollers apply controlled force, the material flows axially and radially, reducing thickness while increasing the rim's strength and structural integrity. This method enhances grain structure, improves impact resistance, and minimizes weight without compromising durability. The precise control over wall thickness ensures superior performance, making flow-formed wheels ideal for high-performance and motorsport applications. After forming, the rim undergoes controlled cooling to finalize its mechanical properties. After the flow-forming process, the rim undergoes a controlled cooling phase to stabilize its structure and relieve internal stresses. This can involve air cooling, water quenching, or immersion in a coolant tank. Proper cooling prevents warping, enhances strength, and ensures dimensional accuracy. The cooled rim is then prepared for final machining and surface finishing.